In this lecture, we are going to discuss about one-dimensional finite square well, and the content of the lecture is from the book A Textbook for Undergraduates by M.C. Jain. So, this is the diagram of the finite square well, and the square well potential shown in this figure is given by Vx, that is the value of the potential is 0 when mod x less than a. That is, when the particle is inside the well, then the potential energy is 0, and Vx, that is the potential, is equal to V0 when mod x greater than a. That is, outside the well, the value of the potential energy is V0. Now, let us consider that a particle of mass m is moving in this potential with the energy E. So, the energy of the particle in this well is E, and we shall consider the case when E less than V0. So, value of the energy is less than V0. If the value of the energy is less than V0, then the particle is confined in a bound state. So, if the value of the potential energy is less than the potential energy given here, so in that case the particle is confined to the well, and it is in a bound state. And it may be that the energy is greater than V0, and when E greater than V0, the particle is unconfined. So, at that case, as the energy of the particle is greater than the this value of the potential energy V0, so particle cannot be confined, and this situation is relevant in the scattering of a particle by a potential, and we will discuss later about this phenomena. So, if we describe the Schrodinger equation, basically the time independent Schrodinger equation. So, inside the well, the time independent Schrodinger equation is minus h cut square by 2m d square psi by dx square is equal to E into psi when mod x less than a. You just check that here the value of the potential is 0, that is why the Schrodinger equation can be written in this format. So, we can write this equation as d square psi by dx square plus small k square psi is equal to 0, where small k square is equal to 2m capital E by h cut square, and the general solution of this equation is psi x is equal to a sin kx plus b cos kx. Now, outside the well, the Schrodinger equation can be written as minus h cut square by 2m d square psi by dx square plus v0 into psi is equal to E into psi, because there is a particular value of the potential energy v0 outside the well. That is why we have written the Schrodinger equation in this way. So, this is for mod x greater than a. Now, this equation can be rearranged like this: d square psi by dx square minus capital K square psi is equal to 0, where capital K square is equal to 2m into V0 minus E by h cut square. Now, V0 is greater than E, we know that because we have assumed the value of the potential in such a way. So, as V0 greater than E, this k square is a positive quantity. Therefore, the general solution of this type of equation will be psi x is equal to c into e to the power minus kx plus d into e to the power kx. Now, the wave function should not be infinite at the position x is equal to plus minus infinite. So, we have to consider this particular condition, and if we consider these conditions, so we must take c is equal to 0 for x less than minus a. So, why it is so? Because you see that for x less than minus a means basically x is negative. So, if x is negative, so this will be positive e to the power minus kx, and if this factor is positive, so at x equal to infinite, what will happen? This term will diverge. So we will take c is equal to 0. And similarly, for x greater than a, what will happen? This term will diverge. So we take that capital D is equal to 0 for x greater than a. So the wave function can be written as psi x is equal to d e to the power kx when x less than minus a. So for x less than minus a, we are considering that the value of c is 0, and for x greater than a, we write psi x as equal to c e to the power minus kx, and inside the well, that is when x is in the range minus a to plus a, then psi x can be written as a sin kx plus b cos kx as described earlier. So these are the solutions of this equation. So this I have already discussed about the fact, that is when x less than minus a. When x less than minus a means at that site x can only be minus infinity, but there is no problem if x becomes minus infinity here. But at that because at that position, what will happen? This factor will be 0. And even you see this situation, that is x greater than a, and that means what can happen as x is in the positive side. So if we put x is equal to infinity here, so what will happen? This factor will be 0, but not infinite. So in this way, the solution of this equation can be described, that is they can be divided in three regions separately. The requirement that psi x and d psi by dx be continuous at x is equal to minus a. We know the condition of the wave function. There is a condition that this should be continuous at some particular point. So from the continuity of the wave function and from the continuity requirement for the psi x and d psi by dx at the point x is equal to minus a, what we can get? You see that at x less than minus a, and the value of psi x is d e to the power kx, and for x just greater than minus a, the value of the psi x is a sin kx plus b cos kx. So we have to consider these two values for applying the boundary condition. So we are applying that condition, that is psi x and d psi by dx, that should be continuous at x is equal to minus a. So let us consider at first the continuity for psi x. So what we have to do? We have to put the value of x is equal to minus a at these two values of psi x, that is this is the first value, this is the second value. So we are writing this minus a sin k plus b cos k is equal to d e to the power minus k. You see that d e to the power minus k, because we have written minus a in place of x here, and similarly for minus a for this x and for this x. So this is the continuity for the psi x, and similarly if we differentiate this psi, that is for d psi by dx, and then apply the continuity at x is equal to minus a, then similarly we can obtain this particular equation. So similarly the continuity for psi x and d psi by dx at x is equal to a gives these two equations. Now we can solve equation 7.48, that means this equation, and 7.50 means this equation, this one and this one. If we solve, then we can get another two equation, that is these two equation, that is equation 7.52 and 7.53. we can get these two equations. Similarly if we solve separately this equation, that is 7.49 and 7.51, then we can have another two equation, that means this one and this one. Now if we use equation 7.52 and 7.54, then you see that in the right hand side this is c minus d and c minus d. So what we will do, we will divide these two equations, and from the division we will obtain k cot k is equal to minus k. And we have written here, that is unless capital A is equal to 0 and C is equal to D. Why? Because you see, in equation 7.52 means this equation and this equation, in the left side there is A. So A cannot be 0, because if A is 0, then left side will vanish. Similarly, C cannot be D, because there is C minus D in the right hand side. So C cannot be D. So to hold this condition, A should not be 0 and C should not be D. So that is why we have written unless A is equal to 0 and C is equal to D. Similarly, if we divide these two equations, that means 7.53 and 7.55, we can also divide these two equations, and from the division we can obtain k tan k is equal to capital K. And here also, to hold this condition, we write, that is unless B is equal to 0 and C is equal to minus D, because for these two conditions either right hand side or left hand side will be 0. So these are the condition to write these two equations. Now we can eliminate k from the right hand side, that is for equation 7.56 and 7.57, we can eliminate the value capital K, and we can write tan square k is equal to minus 1. But you see that this is a square of tan k, so square of something cannot be negative, so this is not possible. Therefore, these two equations cannot be valid simultaneously. These two equations, that means this one and this one, cannot be valid simultaneously. Thus, we have two classes of solution. For the first class, we write that k tan k is equal to k, small k tan k is equal to k. But in this case, this condition can hold, because A equal to 0 and C equal to D, these are not possible for this condition. But for k tan k is equal to k, for this can hold, that is A equal to 0 and C equal to D is possible. And for the second class, that means for this one, k cot k is equal to minus k, this may be true, that is B is equal to 0, C is equal to minus D. So these are the two classes of solution. Now for the first class, the eigenfunction we can write, if we apply this condition, that is A is equal to 0 and C is equal to D, then psi x can be this, because we have already obtained the values of psi x. You see here we have obtained the values of psi x in different zones. But if we write the value A is equal to 0 and C is equal to D, then psi x will be like this for three different zones. And similarly, in the eigenfunction for the second class, if you write B is equal to 0 and C is equal to minus D, then for three different zones, and the value of the eigenfunction will be like this. Now it is interesting to note that the eigenfunctions extend into the classically forbidden region mod x greater than A, because you see that x greater than A, there is some value of the wave function. You see that is for the first class psi x is equal to C e to the power minus kx, and for x greater than A, and the value of psi x is minus C e to the power minus kx. And the distance through which the extension is possible is k inverse is equal to h cut divided by 2m into v0 minus e to the power half, because we know the value of the k, and the distance through which the wave function can extend is this one, k inverse. And this value increases if the value of the energy of the particle increases, if value of E increases. Now we will discuss about the parity. You see that we have obtained two classes of the solution, and we have already discussed about the case of infinite square well in earlier lectures, and there also we have seen that we have obtained two classes of solution, and the first class have even parity satisfying psi of minus x is equal to psi x, and the eigenfunctions for the second class have odd parity, that is psi minus x is equal to minus psi x, and this is possible as the potential energy is symmetric about the origin, that is V of minus x is equal to Vx. Now we will discuss about energy levels. The energy levels can be found by solving the equation that we have obtained, that is 7.56 and 7.57. That is these two sets of equation. If we solve these two sets of equation, and then we can obtain the value of the energy level. But for that purpose we have to a little bit rearrange this equation. We will multiply small a both side of this equation, and also we will multiply a to the both sides of this equation. So after multiplying a, what we will obtain, that is zeta tan zeta is equal to eta, and zeta cot zeta is equal to minus eta. So what is zeta? Zeta is equal to, zeta or xi is equal to Ka, and eta is equal to capital K into A. So for that purpose we have multiplied small a to the both sides of these two equation. So after multiplying, and we have assumed that zeta is equal to Ka and eta is equal to Ka. We have already discussed that what do you mean by small k and capital K. They depend on energy, and we have already told about their respective expressions. So zeta tan zeta is equal to eta, and zeta cot zeta is equal to minus eta. We have obtained these two equations after a little bit of rearranging. Again zeta square plus eta square, that will be you see from this expression, that is small k square plus capital K square into a square. But if we put the values of small k and capital K, which we have already discussed, then this value of this function will be 2m v0 a square by h cut square, and we are assuming that this quantity is equal to gamma square. So gamma will be 2m v0 a square divided by h cut square to the power half. We have that is we have considered that value of this function is equal to gamma square. Now you see the value of the quantity gamma depends on the values of these parameters, that is small m v0 a, and zeta and eta are positive. The energy levels may be obtained by determining the points of intersection in the first quadrant of the circle described by 7.64. If we look carefully, you see that we can draw a circle by considering that this is actually the equation of a circle, because the equation of a circle is x square plus y square is equal to a square, where a is the radius. So this is a parameter zeta square plus eta square. You can consider that this is similar to x square, and this is similar to y square. So x square plus y square is equal to a square. This is the equation of a circle. So we can consider that this is the equation of a circle. So what we can see, we can plot this equation in a particular coordinate system, and if we consider the intersection in the first quadrant of the circle, first quadrant of this circle with the curve 7.62, means this one, zeta tan zeta is equal to gamma. So from the intersection what we will have, we will have a particular state for these two equation, that means zeta tan zeta is equal to eta, and this one, because from the intersection we will have a particular value of these two parameters, that means zeta and eta, and from these two parameters we can calculate the values of the energy. So energy levels can be obtained by determining the points of intersection with this circle to these curves. We will show the figure. So then it will be clear, that is from how from the intersection we are getting the number of states. So let us see the figure. You see that in one axis we have to plot zeta, and in another axis we have to plot eta, so that we can plot a circle. But we will only discuss about the first quadrant. So this is a circle, this is the part of the circle in the first quadrant for a particular value gamma is equal to 1. You see the equation again, that is zeta square plus eta square is equal to gamma square. So for different values of the gamma, we will have different radius of the circle. That is why we have drawn several circles. For gamma is equal to 1, this is the first circle. For gamma is equal to 2, this is the second circle. For gamma is equal to root 12, and this is the third one. So in this way we can get several circles as we are increasing the radius step by step. Now in the same graph, we can also plot this equation. For example, eta is equal to zeta tan zeta, eta is equal to minus zeta cot zeta, again eta is equal to zeta tan zeta. So we can plot these curves. So there will be some intersection of these curves with the circles. You see that for the first circle, this is a interaction of zeta is equal to eta is equal to zeta tan zeta, and for the, but here you see that only one intersection is obtained with this curve. And for the second circle, you see that we have obtained two intersections, that is first for this curve and second for this cot curve, that one for the tan curve and one for the cot curve. And for the third circle, we have obtained three intersections, two for the tan curve and one for the cot curve. So in this way we can get different intersections. So for a given mass m of the particle, gamma depends on the parameters of the square level through the combination V0 a square. We have already discussed that value of the gamma depends on V0 a square, and thus it is a measure of the strength of the potential. As it depends on V0, so sometimes gamma is also called the strength of the potential. It is found that for gamma is equal to 1, there is one even bound state, as there is intersection with the tan curve. That is why we are saying that there is one even bound state and no odd bound state. For gamma is equal to 2, there is one even, that is one intersection with the tan curve, and one odd state, that is one intersection with the cot curve. And for gamma is equal to root 12, there are two even states, that is two intersection with tan curve, and one odd state means one intersection with the cot curve. Thus the three increasing values of gamma gives a total of one energy level at first, then two energy level, and then three energy levels respectively. So we can draw some conclusion that firstly the energy levels are non-degenerate, that is we are obtaining different values of energy for different states. And secondly, the number of energy levels is finite and depends on the strength of the parameter gamma, and hence on V0 a square. And total number of state, that is the as we have described, that is we are obtaining 1, 2 and 3 energy levels respectively. So for generalization we can say that for gamma greater than equal to n minus 1 into pi by 2 but less than equal to n pi by 2, and the total number of states is equal to n. You can verify this because you see, for example, if we put n is equal to 1, then this will be 1 minus 1 into pi by 2 means 0, and this will be pi by 2. So from 0 to pi by 2, as capital N is equal to 1, so total number of states is 1, because you see that we are obtaining one state in the range 0 to pi by 2, see from the graph. Then again from if you set another values of n, suppose capital N is equal to 2, then the range will be 2 minus 1 means pi by 2, and this will be pi. So pi by 2, 2 pi, that means this range. So this range you are obtaining two states. So this is actually generalization. We have already discussed the fact earlier. And as gamma increases, the energy levels correspondingly respectively to even and odd parity appear successively. This means that at first you see that we are obtaining one energy level, means odd, one is odd. Then we are obtaining two energy level, means two is even. Then we are obtaining 3 energy level, 3 is odd. In this way we successively odd even. In this way energy levels will appear. And in the limiting case of infinite square level, V0 tends to infinity, and if V0 tends to infinity, eta tends to infinity, because what is the value of eta? That is eta depends on V0. the value of eta, you see again, if we see the expression of uh, you see that eta is equal to capital K into A. That means this depends on the value of V0. So if V0 tends to infinity, then eta also tends to infinity. And so what will happen if eta tends to infinity, then equation 7.62 and 7.63, you see the right hand side is infinity, and this is only possible for the value of zeta is equal to n pi by 2. If they become zeta is equal to n pi by 2, then right hand side of those equation will become infinite. And for n is equal to 1 comma 2, we will obtain different values of zeta, but zeta is equal to small k into A, and if we put the value of k, and then this will become 2m e by h card square to the power half into A. So if we put the value of eta here, then what will happen, that is, we will obtain the value of the energy E here. So value of the energy E is equal to n square pi square h card square by 8m square. Now if you tally with the tally this value of energy with the value obtained in case of infinite square level, I request the listeners to listen the earlier lecture that is about infinite square level. So in that case, we have shown the value of the energy E is equal to n square pi square h card square by 8m square. So we can obtain the value of the potential energy starting from this derivation. So we can also calculate the value of the energy for the infinite square well. So for that case, the value of the energy will be like this. Further, capital if capital K tends to infinity, when V0 tends to infinity, therefore the eigenfunction 7.60 and 7.61 will vanish for mod x greater than A, as is the case for the infinite square well. So these were also discussed in the infinite square level. So I will also request that is to listen that earlier lecture, so that these parts will be clear. So but the fact is that we can derive the values of energy for infinite square level from the finite square level if we apply these conditions. So thank you all for listening the lecture, and for further understanding I request to go through the textbook of quantum mechanics written by MC Jain. Thank you again.